let me see if I can, oh, I fixed it. Sorry about that. You wish that on the AP exam they asked you which one tastes bitter and sour. That's not a question. Moving on. So blood is a base, and it actually contains a buffer. It stays basic, which is really interesting. Can't wait till we get to buffers. That though. But the thing about blood is you're constantly breathing out CO2, and your body's making CO2 as respiration, and then it carries, your blood carries the CO2 in your body, so you can exhale it, right? Your lungs and stuff. Anyway, CO2 when it dissolves in an aqueous solution makes carbonic acid, but then your blood is actually basic. How does that work? So, it's kind of, are you excited? There's a formula for that on your sheet. Yeah. Alright, so Arrhenius acids and bases, as far as what I have to teach you, it's all about Bronsted-Lowry. But this is kind of where it all started. And it was a good definition. But basically, you're going to see this a lot, HA. This is just saying a hydrogen stuck to something. Okay? Hydrogen stuck to something gives you hydrogen and that something ion. That's what that means. And then this is for base. You have something stuck to hydroxide, and it gives you hydroxide and that conjugate acid of that. Anyway, this was real cute. It kind of worked, but some bases don't actually make hydroxide in solution. So, like I was saying, only true for bases that contain hydroxide ions. There's a lot that don't have hydroxide, but still are going to make solutions basic. The most kind of common one of that is ammonia. So ammonia is a base, but it doesn't, I mean, it's NH3. There's no oxygen in there. So this is only true for reactions that take place in aqueous solutions. Most of the ones that we'll be doing are going to happen there. So Bronsted-Lowry comes along. These are two different guys. But basically, didn't mean to do that. I'm going to stop doing that. Just make up jokes. I don't even mean to anymore. Acids donate protons. If you don't know what a proton is, let's think about this, okay? So where I am. Look at hydrogen up on that periodic table. It's got a number 1 for its atomic number and a 1 for its mass. How many neutrons has it got? How about none? So how many electrons does it have? 1. So if you have an H+, that means, like a positive ion means you have a proton without a button. A proton is the hydrogen ion. So when we're talking about protonation, donating protons, I'm talking about hydrogen ion. That's what I'm talking about. And hopefully you pick that up from your homework, but I don't assume anything anymore. So anyway, this is a proton. This guy, this is this. That's a proton. And like I said, hydrogen doesn't have any neutrons. It loses an electron. You have 1 proton left. And so the acid's the same as Arrhenius. The bases accept protons, and so when you look at a base and it goes through a reaction, on the product side it's just going to have an extra H. That's all that's going to happen. So it works for most acid-base reactions, and this is the one that we're going to use. So, alright, so these things, look at here at this little reversible reaction. See that? Hopefully last unit got you used to thinking about reactions not just going forward, they also can be reversible, and the reverse reaction can happen. And sometimes reactions favor the reactant side. If the remember, if the Ka, well, sorry, I'm already in acid mode, but if the equilibrium expression, if you solve it and you get your K value is a very small number, it actually favors the reactants. And if it was a big number, it favored the products. Remember, little number means it favored the left, and a big number was the right. I'm reminding you of things you already know, hopefully. Anyway, so the thing about this, yes, I have this acid. If I watch this acid from the reactant side to the product side, I'm going to watch it, and what's going to happen is it's going to lose H. Whee! And notice that it has a minus sign. That's because it lost an H+. Well, see how that leaves this guy like needing a plus sign, and you know, so anyway, this base, if I watch it from the reactant to the product side, it could be anything. It could be a huge, long CH, OO, whatever, blah, blah, blah. Doesn't matter. On this side, it has all that stuff, and on this side, it has all that stuff and then an H. That's all you have to look for. They're going to throw crazy stuff. Don't be worried. So the base on this side is going to be that B, whatever it is, and then it has that H, and it'll be positive. So then if we look at it, we can go in reverse. if I go from here back to the beginning, well, this guy got an H, didn't it? So if you accept a proton, if you accept an H, well, then you're a base. So in this case, this is a base now. This acid makes a conjugate base. And so on the movie, he was talking about, oh, it was one of the what is it called, crash course videos, and he's like, this word comes from the conjugate, like conjugal visit. And so these are like very intimate friends. So the acid and the conjugate base, those are the one and the same as the reaction goes forward and reverse. And then the base, when it accepts a proton, there's your H that you're looking for, and then also the reverse reaction, you can donate an H. How does that make you feel? This is okay, right? Okay. I'm trying not to laugh. It's not funny. So what is what here? So take a second and work with your table and try to, and this is what I want you to do. For acid, just put an A, for base put a B, and for conjugate acid put CB, and for conjugate acid, well, the other one, put C, you know what I mean. Put a C in front of it for conjugate. And I'll give you a second. I think this is on your acid and base, so, you know, of those 40 questions you're going to see, like, you can totally get that one right. So notice that water is amphoteric, and so it can act as an acid or base because it can accept a proton and it can donate one. Listen to me, and I'm sure I'm going to say this again. Anytime that you see these expressions and they just have an H+, that's not a thing. That H+ is really stuck to a water, and I'll probably end up drawing that. You know what? I'm going to draw it right now. So if we look at water, do you remember that water is sort of bent, and then it has two lone pairs? Remember that? So if I have a hydrogen, what ends up happening is the hydrogen will actually get right there, and then I'll have two lone pairs. And then it takes on a 1+. Because if you add up all the electrons in this picture, I have 2, 4, 6, 8. And I'm only supposed to have 1, 2, 3. So I'm not supposed to have 9, and I have 8. Right? So I'm missing one, and that's the plus sign. Did I lose you on that? I didn't say that like the best I could have said. I could say, I'll try again. I have 8 electrons in this picture, yes? And then, like, if you look, these guys all brought 1 to the party, and this guy brought 6, and so I should have 9. I'm missing 1. So this is that. There's no H+ that's floating around in water. You have hydronium floating around in water, and then you just put the H as easier. All right. So strong acids dissociate completely. And when I say dissociate, I mean they ionize completely. They break apart completely. The Ka values for hydrochloric acid or nitric acid, they are like whatever times 10 to the positive 5th, positive 6. They're in hundreds of thousands or millions. They go all the way to the product side. They're not reversible. And so if you look at the reaction, it doesn't get a reversible arrow. They're not coming back. They go and they don't come back. Weak acids and also weak bases, they're going to partially dissociate. So that means that some of them are going to donate a hydrogen or accept a hydrogen, but they totally can go back. And depending on the stresses you put in the system, they can go back easier, back to the reactant sign. And we'll get to that. So only weak acids and bases, though, get this reversible reaction arrow. Strong acids and bases, those 6 that you had to memorize. Did y'all watch the video with the nitric? Did you do that? Well, that was handy, I thought. How'd you oh, okay. Such a good singer. So if you don't know the strong acids, these are them. Basically, you have everything in your group 17. This is a trick one, okay? So hydrofluoric is not a strong acid, and so hopefully yesterday your POGL helped you with that. But notice it's the other ones in the group 17. But then you got perchloric, nitric, and sulfuric. So anyway, those are those. So you do need to memorize those. Your strong bases. When she was singing, did you catch that part about them making a V? Okay.
Yeah.
I know, like, this is the best ever. So in case you missed it, it just goes right here.
It goes all the way down to C.
Oh, yeah. Oh, that is right. Let me just explain to you that. But you're right. But it goes down to here. I don't even like doing that. You will see some barium hydroxide. I'm such a liar. But there, okay? This. There's the B. See how it makes B? Sorry, I missed the ball. Anyway, so, yeah, on my thing right there, it says that. How nice of me. And then I guess francium hydroxide is strong. Yeah, that's not a thing. So, a lot of your weak bases will contain nitrogen, like I just said about ammonia. Ammonia has nitrogen. So, you'll see those NHs and they'll be hanging out. Don't let it scare you. It's fine. This doesn't matter. You're going to look at the formula. You're going to look for an H missing and get an H, and that's fine. Don't let that intimidate you. Do y'all remember that one that I did on the FRQs, and you had a really long hydrocarbon chain, and it had its boiling point, and a shorter one, it had its boiling point, and the boiling point for the longer one was higher because it had more London dispersion forces? The grader, one of the guys that was teaching, he was the table leader for that, and he said that so many kids just left that blank and put, "We didn't learn organic chemistry." He said he saw probably 10% of the kids either leave it blank or wrote, "I don't know organic chemistry," because it looks, if you didn't go over that, like, that would be super intimidating. But I mean, so don't get intimidated by these long formulas. Just look for the H's, okay? So strong. This is important. Strong acids are going to have very weak conjugate bases. I know that doesn't sound important right now, but later on when we do titrations, like if we mix a strong acid and a strong base, the equivalence point for that is going to be 7. You're going to make water and the salt won't affect pH. If you titrate a weak acid with a strong base like sodium hydroxide, your equivalence point where they're equal, it might be 8.5 for the pH. Because a weak acid is going to make a weak conjugate base, but it'll be strong enough to change the pH. And I don't expect you to understand what I'm saying right now, but it's important that you understand this that I'm saying right now. So a strong acid is going to have a very weak conjugate base. Very weak conjugate bases have very strong conjugate acids. And then a lot of the stuff that we talk about, like acetic acid or ammonia, yeah, they're weak, but they're kind of mid-range. They're strong enough to do something. I mean, you don't want to go like hang out in some ammonia. But like, for example, sodium and chlorine and water, that ain't a big deal. And those are the conjugate acids and bases of hydrochloric acid and sodium hydroxide. Like, we had some stupid strong hydrochloric acid left from the lab the other day. It's like 12 molar, and we didn't put it back in the jug, but the gas leaves, and so I couldn't put it back because I don't know the molarity. But all I've been doing every day is just throwing some sodium hydroxide in there. And I ain't scared of it. You know why? It's making salt water for me. Every day I test pH to like 1, so I like to do more sodium hydroxide. But there's not scary to me, but I do need to neutralize it. So I'm like, some more. Hopefully one day it'll be right. I think, what are we on, like day 4 of trying to neutralize that now? So anyway, so if I look at this, this is what I was saying to you. So I have my really strong acids. These are my hydrochloric and nitric acids. You know, hydrofluoric acid is not a strong acid, but it's not super weak, you know. But the conjugate base, I mean, this isn't going to change pH at all. Not changing the pH, changing the pH a little bit, and then as I go down, it will change the pH a lot more. And so as acid strength increases, your conjugate base strength, there we go, your conjugate base strength decreases. I went in a circle and it didn't work out for me. Are y'all okay with that? Okay. Whee! So the stronger base is always going to accept the most protons. And then there's always going to be 2 bases. There's going to be the base on the reactant side, and then you're going to have the conjugate base. I feel like I already did that about 3 times, so I feel like I'm all right with that. And so right here, if I follow my hydrogen, where does it go? It's going to go from this hydrobromic acid, and then it's going to hop on that lone pair space that I showed you, and it's going to make the hydronium and that bromine ion. H2O and Br minus, they're going to compete for protons. and water's going to be the strongest base, and so it's going to get that hydrogen, right? So that's what you get. And this is one of my strong acids, so it's not going to go, the reverse reaction isn't going to happen. So weak acids have strong conjugate bases. So my ammonium, H2O and ammonia compete for protons. Ammonia is the stronger base, even though it's not a strong base. All the strong bases have hydroxide in them, every single one. Okay, so this, even though it's a strong base, it's not one of the strong bases. It's a medium strength. But it's a stronger base than water, so it is going to get the hydrogen instead of the water. Whee! All right, so why are some acids stronger than others? This PowerPoint through here, I don't like it. I feel like the Pocal did a better job. So I just want to like take a break from this, and I'm going to on here. But if I'm looking at a molecule, and I just have, maybe there's one. I just talked about that. I'm going to cross my fingers and I'll draw one because I'm super good at drawing. Not really. So this hydroxyl group right here, wow. This guy, it's this single hydrogen that gets pulled off, and then you're left with this oxygen without it. So if you're looking at a picture, and then make that fix. There. If you're looking at a picture and you want to kind of see what's going on, did it lose a hydrogen? It's going to, when I say hydroxyl, it's just the hydroxide group. It's the OH. It's not called a hydroxide group. It's called a hydroxyl group. But it's this hydrogen that gets stolen away from that oxygen. So if you're bonded to something like chlorine right here, it's going to be pulling all this electric negative, making up stuff. This kind of negative charge away from the hydrogen. It's just going to be easier to steal. That water's going to come along. It's got its own little oxygen, and it's just going to be like, hey, come get on my home here. It'll be fine. So I don't like this part. That doesn't help me. So this is what I just explained. Just ignore all this. I do like this one here. This is kind of what I was showing you. So it's this oxygen that's going to get removed when you go to make your conjugate base. And so notice all the oxygens over here that are sort of pulling that charge away from the hydrogen, and the water's going to come along and be like, come on. And over here, you don't have as many oxygens kind of pulling that charge away from the hydrogen. Are you okay with this idea? Cool. Oh, we got to get to that math part. Carboxylic acids, a carboxyl group is COOH. And so when you see an acid and it's written like blah, 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 COOH, and you're like, why didn't you just write CO2H? Because this oxygen ain't doing the same thing as this oxygen. That OH on the end tells you, hey, there's a hydroxyl group, and it could be an acid, and that's that helps you. So a lot of times you'll see this, like acetic acid has this on there. And you see that COOH, and you're like, what the heck? Like, that's why. Okay. So a lot of y'all would ask me about that, earlier in the year. Let's see. How are we feeling here? Stronger. Oh. So there's my hydroxyl group. And so if I look at everything getting pulled away so I can remove this hydrogen, I got 3 fluorines versus 3 hydrogens. So of course the fluorines are going to pull everything toward the left, and then the water's going to be able to remove this hydrogen. I feel like I'm beating a dead horse. You okay? R stands for like CH3, all the way, keep going, long hydrocarbon chain. Autoionization of water. I texted you guys. I don't know if you opened it. But having this in your calculator, 1 times 10 to the negative 14th. I don't know if you actually did that, but I totally did it when I did about half your homework, and I was just like, wait a minute, there's that button where you can do this. So then I programmed it. It made my life a lot better. But this is a very common thing that we're going to come back to, even not today, later. So just basically water chilling out in a beaker at 25 degrees. At any one point in time, you're going to have 1 times 10 to the negative 7th hydroxide ions floating around, and your concentration of hydronium is going to be the same. And it's going to have a pH of 7 because your acid and base is the same, but you're still going to have some ions in there. And so this little trick, it's not even a trick. If you're given the hydroxide concentration or you're given hydrogen concentration, you can solve for the other one because you know this side of the equation. That's a very common kind of question. I didn't get any concerns from your homework on that. Seemed like most people got that. But like I said, you know, from h, if you take and you multiply exponents, you're going to add them. And so -7 plus -7 is -14. 1 times 10 to the -14. Then I believe this is on the formula sheet, right? The hydrogen ion concentration. Okay, so anyway, memorize it or just program it into your calculator. You can program whatever in your calculator. They don't check your memory and they don't delete it when you're done. So, I mean, there's not anything really to program, but there are 2 equations like the Arrhenius equation and the Nernst equation. They'll take credit for doing the math instead of like drawing circles. And so we'll kind of cross that bridge when we get there. But there's some formulas that we might want to put in there that is fine. I mean, if you have a graphing calculator, because you can have one, you can. So here's an example. The concentration of hydroxide in solution is found to be 1.4 times 10 to the 11th molar, and it wants you to find, you know, the hydronium ion concentration. Know here that they could totally be like find the hydrogen ion concentration. You can write this either way. This is just faster, but that means that. And so go ahead and fill in this example. What?
It's already filled up.
Oh, it's already filled in? Okay. So basically, you just going to rearrange and then divide by the hydroxide ion concentration, and then you get 7.1 times 10 to the -4th. That, to me, this is okay. This is just to give you like a little psychic vision of your future. This is what you're going to do after you do a lot of other things. It's like the end part of it. So acid-base equations can be written, and I kind of just did this. I explained this about 5 times a second ago. Water, because this is all going to be equilibrium. Remember, pure solids and pure liquids, they don't go in an equilibrium expression anyway. So you don't have to write the water. I like to write it, but you don't have to. If you write the water, then you need to write hydronium. If you don't write the water, then you write hydrogen. Okay, so you can. It's both the same thing. pH. What does this mean? pH means power of hydrogen, and so it turns out that when you calculate pH, don't you have to take the negative log of the hydrogen ion concentration? So if pH stands for power of hydrogen, it actually literally is the power of hydrogen on a 10 with a negative sign, and that's your pH. And so that's pretty interesting. And so negative power 10. And so if I have something right here, this was your warm-up. If my hydrogen concentration is 10 to the -4th, then your pH is 4. You're going to have to be able to do that in your head, but I don't think that's a problem. Hopefully. Anyway, so the pH of pure water at 25 degrees. So if I had the Kw is 1 times 10 to the -14th, you know, you're going to need to know the concentrations of both those. Can you see how this is x squared if they're equal? X squared is equal to that. So this one's pretty simple. So the pH of pure water is 7. I don't think I've told you anything mind-blowing there. You okay? Y'all look bored. That's good. Remember that face later. So if a solution has a pH of 5.63, find the hydrogen ion concentration. So this is where people maybe struggle like a little bit. So do you have this filled in on your paper? Okay, so let's do this together. So pH is equal to the negative log of the hydrogen ion concentration, and it wants me to find this. So I'm just going to fill in what I know. So 5.63 is equal to the negative log of my hydrogen ion concentration. This is where you're going to screw up. You listening to me? This is where, if you're isolating a variable, okay, let me ask you something. If I had 2 times log, and then this, before I could, this is basically your x. Before I could solve the x, I mean, don't I have to do something with that 2 first? Sure do. You got to divide both sides by 2. So you got to get rid of that negative sign before you do anything, or your answer's going to be wrong. So I'm going to basically, before I do anything, Well, okay. I'm going to divide both sides by -1. And that, I mean, this isn't really like in the notes, right? They just kind of assume that you do this step, but you got to do it, okay? So I have -5.63 is equal to the, I almost did it, the log, just ignore the fact that that log was so crazy, the log of the hydrogen ion concentration. And to make this log go away, what I'm going to have to do is I'm going to have to go 10 to the -5.63 is equal to H plus. When I take and raise 10 to a power of log, like that's 1. Okay, so that's how you make logs go away. You've been in that algebra class, right? Calculus people for the win, right? I know y'all do this, don't you? You know how I made your seating chart? It's real hard. I put somebody in calculus at each table, and then Drew, you're in AP Stats. I figured that was good enough.
You said 1 for.
I know your table got 2.
Yeah.
It's rigged. It's unfair.
No, I put a lot of thought into this. I'm pretty proud of this seating chart. So anyway, you got to plug this into your calculator, or no, I don't want to do it. You can plug this into your. It's the other way that you don't get a calculator. This guy, you're gonna get a calculator. So, 10 to the -5.63, and you get 2 point. Oh, I need to tell you about Sig Figs. Okay, pH. This has 2 Sig Figs. Did you hear me? The numbers after the decimal are your Sig Figs. So my hydrogen ion concentration can only have 2 Sig Figs. So 2.3 times 10 to the -6. And I've been looking through like the Princeton book and some other practice exam kind of things, and they don't follow that rule, but that's totally the rule. And the guy that was the table leader that helps to write the test, he said here's the rule they use for Sig Figs. He said that Sig Figs can only be one part of one 10-point question, and it'll always be related to measurements, like on a beer lead. Right? So, and then if you miss it, it's 1 point of a 10-point question. So it's basically 1 point out of 100 points, and that's all they can do. And it'll always be plus or minus. And if you do the math, this is crazy. If you do the math, 3 Sig Figs, they've never on an AP chemistry exam asked something without 2, 3, or 4 Sig Figs. That's always the answer. So if you use 3 Sig Figs, you'll always be within plus or 1 minus. Did you hear me? That's cool. So just practice 3 Sig Figs from now on. You won't ever be wrong. But that's how to do it. I mean, that's how it goes. That man stood up there and said it like very confidently, and I believe him. He's pretty smart. No, yeah. He's like, and you know, I asked him a question because I had noticed on the free response there was 1 electrochemical, 1 titration, 1 lab technique, then a molecular force, and then kinetics and stuff in the small ones. And I said, I noticed that pattern as I looked at the core release exam. Can you tell me anything about that? And then he kind of blushed and smiled, and he said, there is a pattern forming, and they're going to continue to use it in the future, but I can't talk about it because I'm on that committee. So we got it all figured out. Anyway, so that your hydrogen ion concentration is 2.3 times 10 to the -6. Just remember to do that thing where you divide by -1. Because if you put 10 to the 5th, 10 to the 5.63, and then you try to hit like negative log on your calc, that ain't gonna work, okay? So I did, and they don't show that step. Anyway, so that's how to do it, the end. So I don't know why they're showing you this formula like on the next page, but there's the pH formula. pH is the negative log of the hydrogen ion concentration. They're making this look way too crazy. Just use your formula sheet, okay? Stop looking, avert your eyes. So here's your warm-up, and I'm going to show you this. I'm going to show you the math for it. So 0.1 molar HCl, its pH is actually 1, and the pH of 1 molar HCl is 0. Do you want me to show you how? I'm kind of excited about this. I don't get out much. So, can we agree? Okay, 0.1 molar HCl. What is the hydrogen ion concentration if it dissociates completely? How about 0.1? Did you get how I did that?
Yeah.
I know, I'm a magic witch. Don't care. pH is equal to the negative log of the hydrogen ion concentration, which is 0.1, right? So if I, well, you can plug that in, but I don't know. So this is basically, on a 10, it's a 1, and then, I feel like I'm doing this wrong. I had it all figured out.
Yeah, let's see what you're saying.
Negative log 0.1 is 1.
Oh, right.
Yeah. Let's just send it first.
Oh, this is
Yeah,
that.
that's right.
That is right. Okay, good. I was like having one of those moments where you're like question your life. I was like, this is a -1, but the answer's 1. Because I knew the answer. Yay! 10 to the -1. I teach scientific notation. Like, I do that for fun. Like, I totally know this. You trust me? I taught you this. So, anyway, the log of 1, right? This is 10 to the what, right? So 10 to the what gives me 1? 10 to the 0. See, that's how you do that. Well, y'all looking like y'all don't know. You didn't know what I'm doing now, did you? Okay, I'm just saying. Oh, I got that. That's so easy. And so the same thing with the sodium hydroxide. You get the pH of the sodium hydroxide becoming 13 and 14. And really the POH is easy to do in your head, then subtract from 14. So it comes out the same. Do you know that POH is plus pH is 14? Is that something for your homework? I thought so. Just checking. I'm going to use my clock voice now. I just did this. So what you do right here is you, if I have 2.5 molar, then that's my hydrogen ion concentration. There's a whole, for a weak acid or a weak base, you actually have to use an ice table. Isn't that fun? But for a strong one, I know you made a face, that was funny. For a strong one, you actually just fill in the molarity. And do you have these on your paper? Got them? How do you feel about, how does this make you feel?
That's because it dissociates.
Yeah, so if you have 1 molar HCl, that means you have 1 molar H and 1 molar Cl. Just not a little. I think that I want to do this tomorrow. I'm going to let you, I need to check your Sig notes and grade your quiz, which I don't know if I can do all that in 7 minutes. But what I'm going to do, I want you to work on, I'm going to try, and I probably can do it. For your homework, you're going to do everything in this packet ever, unless I tell you not to. But for right now, and it's okay that we're like a little behind because I like have extra time scheduled into this unit because I'm not going to play. So go ahead and do for me. Stop at, so you can actually go through 15. These are really easy. They really are. So for conjugate acid and bases, you can use the CA and A and all that. But that's what you have to do tonight. That shouldn't take you very long. And of course,